Picture a night sky so crowded with stars that 7 suns rise together, their orbits tangled in an intricate dance of gravity and light. This isn't science fiction, it's the reality of septuple star systems, some of the rarest and most bewildering cosmic arrangements we've ever discovered. Most of us are familiar with binary stars, where 2 suns circle each other, but 7 stars bound together in a single system that defies everything we thought we knew about how stars form and survive. These celestial oddities are so unusual that spotting one feels like finding a cosmic needle in a haystack, and when astronomers do, they often uncover mysteries that rewrite the rules of astrophysics. What makes septuple star systems so fascinating isn't just their rarity, it's the sheer chaos of their existence. Imagine the gravitational forces at play, the way these stars tug at each other, some locked in tight orbits while others swing wildly through space. The stability of such a system seems impossible, and yet, against all odds, they endure. Scientists are still piecing together how these stellar families could even form without tearing themselves apart. Some theories suggest violent stellar collisions in the distant past, while others point to intricate gravitational dances that somehow found balance. Every discovery in these systems challenges our understanding of star formation, leaving astronomers both thrilled and baffled. But the real magic lies in the strange, unexpected details that emerge when we study these cosmic marvels. From stars that behave in ways no model predicted to bizarre planetary formation scenarios that shouldn't exist, septuple star systems are treasure troves of astronomical anomalies. Over the next few minutes, we'll uncover 30 of the most astonishing discoveries about these systems, phenomena so peculiar they'll make you question what else might be hiding in the depths of space. Whether it's stars that seem to defy physics or the mind-bending ways light and gravity interact in these chaotic environments, prepare to have your curiosity ignited. The universe is stranger than we ever imagined, and what you're about to learn will leave you staring at the night sky with fresh wonder. The first confirmed septuple star system, known as AR Cassiopeae, sent shockwaves through the astronomical community when researchers finally pieced together its staggering complexity. Located roughly 4,000 light-years from Earth in the constellation Cassiopeia, this system wasn't identified overnight. It took decades of observation and technological advancement to unravel its secrets. Early telescopes could only detect the brightest stars in the group, leaving astronomers puzzled by strange fluctuations in light and motion. It wasn't until the advent of high-resolution spectroscopy and precision radial velocity measurements that the full picture emerged: 7 distinct stars, bound together in a gravitational web so intricate it defied conventional models. What made this discovery so groundbreaking wasn't just the number of stars, it was the way they interacted. Unlike simpler binary or triple systems, AR Cassiopeae revealed layers of orbital hierarchies, with pairs of stars circling one another while simultaneously orbiting other pairs in a dizzying celestial choreography. Confirming this arrangement required untangling overlapping light curves, deciphering Doppler shifts from multiple stars simultaneously, and accounting for gravitational perturbations that shouldn't have allowed such a system to remain stable. Skeptics initially dismissed the data as instrumentation errors or optical illusions, but as evidence mounted, the reality became undeniable. Nature had engineered a stellar arrangement far more complex than anyone predicted. The challenges astronomers faced in verifying AR Cassiopeae revealed just how much we still don't understand about star formation. Traditional theories suggested that systems with more than 3 stars should be inherently unstable, their gravitational interactions inevitably flinging members into space over time. Yet here was a system with 7 stars persisting for millions of years, forcing scientists to reconsider everything from protostellar disk fragmentation to the role of dark matter in shaping stellar nurseries. This single discovery didn't just add a new oddity to the cosmic catalog, it fundamentally expanded our definition of what's possible in the universe. One of the most bewildering aspects of septuple star systems is the sheer unpredictability of their orbits, a gravitational ballet where chaos reigns supreme. Unlike our solar system, where planets follow stable, predictable paths around a single star, these systems resemble a high-stakes game of cosmic pinball, with 7 massive bodies constantly pulling, twisting, and destabilizing one another's trajectories. Take the system Nu Scorpii, for example. Observations reveal stars that should have been ejected long ago, yet somehow cling to the group, their paths zigzagging wildly as they're buffeted by competing gravitational forces. At times, one star will abruptly accelerate, slingshotting around another in a maneuver that defies conventional orbital mechanics, only to be yanked back into the fray moments later. These erratic movements aren't just theoretical. Telescopes have captured stars in these systems making sudden, violent detours, as if an invisible hand keeps rearranging the celestial chessboard. How do such unstable systems avoid flying apart? The answer may lie in a delicate balance of distance and timing. Some astronomers suggest hierarchical arrangements, smaller, tightly bound groups of stars orbiting each other at a safe remove from other clusters within the system. Picture a set of nesting dolls, 2 binary pairs circling one another slowly, while a distant trio interacts just enough to stay gravitationally tethered without causing catastrophic disruptions. Others propose that these systems are temporary, caught in a fleeting moment of equilibrium that could collapse any time over the next million years. There's even evidence that magnetic fields or circumstellar disks might act as cosmic shock absorbers, dampening the violent interactions that would otherwise tear the system apart. Perhaps the most striking revelation is that chaos itself might be the stabilizing force. In certain septuple systems, the very unpredictability of the star's motions could prevent any single body from gaining enough momentum to escape. It's counterintuitive, but the constant gravitational jostling might distribute energy so evenly that no star accumulates the velocity needed to break free. This delicate dance of push and pull challenges our assumptions about cosmic order, proving that sometimes the universe thrives on controlled anarchy. The more we study these systems, the clearer it becomes. In the realm of septuple stars, the rules aren't just bent, they're rewritten with every orbit. Among the 7 stars in these chaotic systems, the temperature differences can be staggering. Imagine standing between a blowtorch and an ice sculpture, while both somehow share the same backyard. In one septuple system, astronomers have measured stars with surfaces blazing at over 50,000 degrees Celsius alongside dimmer companions barely cracking 3,000 degrees. That's like having a stellar furnace orbiting next to a cosmic campfire, and it creates an environment where the laws of physics seem to bend under the strain. The hottest stars, often blue-white giants, flood the system with intense ultraviolet radiation, while the cooler red dwarfs emit barely a whisper of infrared warmth. This isn't just a curiosity, it reshapes everything we thought we knew about how planets might form in such extreme conditions. Take the system HD 8887, where 3 blue supergiants dominate with temperatures so high they could vaporize rock at distances 10 times farther than Earth is from our Sun. Yet tucked between them, 4 smaller red dwarfs smolder at barely a fraction of that heat. The radiation pressure from the blazing giants should have shredded any chance of planet formation, yet preliminary data hints at dust disks, potential planetary nurseries orbiting some of the cooler stars, defying all expectations. How could solid material coalesce in such a hostile environment? Some researchers suggest the cooler stars act as shields, their gravity wells creating pockets of relative calm where dust particles might cling together. Others propose that the violent stellar winds might actually compress distant debris into dense rings, triggering planet formation through sheer force. These temperature extremes also rewrite the rules for habitability. A planet theoretically orbiting at the right distance from a red dwarf in one of these systems would face not only the dwarf's frequent solar flares, but also intermittent blasts of radiation from its searing siblings. The day-night cycle would be a nightmare of scorching heat and sudden deep freezes, with potential atmospheres ripped away by competing stellar winds. And yet, simulations show that under specific albeit unlikely alignments, temporary stable zones could arise, offering fleeting windows where liquid water might exist. It's a reminder that life, if it dared to emerge here, would need to endure conditions far beyond anything we've seen in our own solar system. What fascinates scientists most is how these thermal contradictions force us to reconsider star formation itself. Normally, stars in a cluster share similar temperatures because they're born from the same molecular cloud. But in septuple systems, the gap between the hottest and coolest members suggests a far more dramatic origin story. Perhaps a cosmic collision where two distinct star clusters merged, or a rare case of multiple generations of stars trapped together by gravity. Every new observation peels back another layer, revealing a universe far more inventive and far more unpredictable than we ever imagined. Rare eclipsing septuple systems offer astronomers a cosmic shortcut to unlocking stellar secrets, like nature itself handing them a magnifying glass. While most septuple stars remain too distant and tangled for detailed study, a handful align so perfectly with Earth that their stars periodically eclipse one another from our vantage point. These fleeting moments when one star passes in front of another transform an otherwise indecipherable blur of light into a treasure trove of data. By measuring how the light dims and changes during these eclipses, scientists can tease out precise details about the star's sizes, masses, temperatures, and even their atmospheres, details that would otherwise stay hidden in the glare of 7 suns. One of the most studied examples is the System V994 Scorpii, where 3 separate pairs of stars eclipse each other in overlapping cycles, while a 7th star looms in the background like a silent participant. When one of the hotter, brighter stars slides behind a cooler companion, the dip in light isn't just a simple flicker, it's a nuanced reveal. The way light filters through the outer layers of the eclipsing star exposes the composition of its atmosphere, while the duration of the eclipse pinpoints the star's exact diameters with astonishing accuracy. These events are so precise that astronomers have even detected subtle distortions in the star's shapes, caused by the relentless gravitational tug of war between them. But the real magic happens when multiple eclipses overlap in these systems. Imagine 2 stars eclipsing each other while a 3rd star's light curves around them due to gravitational lensing, bending the signal like a cosmic funhouse mirror. These compounded distortions create light curves so complex that decoding them feels like solving a 7-dimensional puzzle. Yet every twist in the data leads to breakthroughs, confirming predicted orbital angles, revealing unexpected stellar flares, or even hinting at undiscovered bodies lurking in the system. In one case, an anomalous blip during an eclipse turned out to be a rogue planet spiraling through the chaos, its presence betrayed only by the shadow it cast on a star's glowing surface. What makes these eclipsing systems so invaluable is their defiance of simulation. Computer models struggle to replicate the intricate gravitational ballet of 7 interacting stars, often producing results that crumble under real-world observations. But when nature provides a ready-made laboratory, a system where stars literally cross paths on cues, scientists gain a rare chance to test theories against reality. Each eclipse is like a cosmic experiment, offering insights into stellar evolution, mass transfer between stars, and the stability of multi-star orbits. The data gathered here doesn't just apply to septuple systems. It reshapes our understanding of all multiple star systems, proving once again that the universe's greatest mysteries often come with their own built-in flashlights. Dust disks around stars usually signal the birth of planets, a swirling nursery where particles collide and clump together over millions of years. But when these disks appear in septuple star systems, they don't just defy expectations, they seem to break the rules entirely. In most multi-star setups, the gravitational chaos shreds debris into diffuse, uneven rings or scatters it entirely. Yet astronomers have spotted dense, structured dust disks orbiting individual stars within these 7 sun frenzies, their edges sharp and their shapes oddly pristine, as if untouched by the surrounding turmoil. How can such delicate structures survive in an environment where gravitational waves should rip them apart? The disk around the central star in the septuple system Ty Coronii Australis is a perfect example. Observations reveal a ring of dust and gas so well defined it could rival the protoplanetary disks found around solitary young stars. Spectral analysis shows it's packed with silicate grains and frozen carbon monoxide materials that typically glue together to form planetary cores. But here's the twist. This disk exists just 2 billion miles from 4 other stars, each tugging at it with enough force to fling its contents into space. Conventional models insist such a disk should have been disrupted within a few thousand years, yet it persists, suggesting some unseen mechanism is shielding it. One theory points to magnetic fields weaving an invisible cage around the disk, while another proposes that the star's competing gravitational forces might, paradoxically, create temporary pockets of calm where material can settle. Even stranger are the disks that shouldn't exist at all. In the system HD 1,560,828, 2 stars share a single debris disk, a cosmic carousel where both stars orbit inside the ring, not around it. Normally, this arrangement would be unstable, with one star's gravity stripping material from the other. Yet this disk shows no signs of decay, its particles moving in synchronized patterns that baffle physicists. Some researchers speculate the star's orbits might be synchronized just precisely enough to balance their destructive pulls, like 2 dancers spinning a ribbon without ever tangling it. Others wonder if the disk is constantly replenished by collisions in a hidden reservoir of comets or asteroids, a scenario that would require a level of fine-tuning bordering on the miraculous. What these dust disks reveal about planet formation is even more startling. In quieter systems, debris gradually coalesces into planets over predictable timelines. But in septuple systems, the process becomes a high-stakes gamble. Simulations suggest that any fledgling planets here would endure bombardment from redirected asteroids, violent shifts in orbital paths, and blistering radiation from multiple stars. And yet the presence of these disks implies that somehow, against all odds, some material survives long enough to clump together. Could planets in these systems form faster, their chaotic environment accelerating collisions? Or do they arise only in fleeting moments of stability, like sandcastles built between crashing waves? The implications stretch beyond these systems. If dust disks can thrive in such extreme conditions, it forces astronomers to reconsider the limits of planetary birth elsewhere, even in seemingly hostile environments like globular clusters or near supermassive black holes. Every unusual disk found in a septuple star system isn't just a curiosity. It's a challenge to the textbooks, a reminder that the universe has a flair for building order out of chaos. As one researcher put it, these disks aren't just surviving the storm, they're teaching us how to dance in it. If you were to gather 7 siblings in a room and discover they spanned multiple generations, some barely teenagers while others were nearing retirement, you'd assume they came from different families. But that's exactly the kind of paradox astronomers face when studying certain septuple star systems, where stars bound by gravity show age gaps spanning hundreds of millions of years. Conventional wisdom says stars in a system should be twins, born from the same collapsing cloud of gas and dust within a tight time frame. Yet systems like NGC 2668 shatter that assumption, with spectral analysis revealing stars as young as 50 million years old orbiting alongside relics over 700 million years their senior. It's like finding a kindergarten student and a college graduate sharing the same birth certificate, and astrophysicists are scrambling to explain how such a family tree could exist. One leading theory suggests these systems aren't born together at all, but are cosmic patchworks assembled through violent encounters. Picture a stellar nursery where two distinct star clusters, each with its own generation of stars, collide and merge. Gravitational chaos during the merger could weave them into a single system, trapping stars of wildly different ages in a shared orbit. The Septuple system HD 1,580,726 supports this idea. 3 of its stars show lithium abundances typical of youthful stars, while the other 4 exhibit heavy element ratios only possible after billions of years of nuclear fusion. The stark contrast implies these stars originated in separate regions of the galaxy before fate, and gravity stitched them together, but there's an even stranger possibility. Some stars in these age-gapped systems show chemical signatures hinting at a far darker origin, stellar cannibalism. In the system Aer Cassiopeiae, one middle-aged star bears traces of elements usually found only in supernova remnants, a clue that it might have absorbed material from an exploded companion. If true, it suggests some septuple systems started with even more stars, only for a few to meet violent ends, leaving behind survivors of different ages. This would make these systems less like families and more like gravitational support groups, where stars of disparate ages cluster together in the aftermath of cosmic trauma. The implications ripple beyond mere curiosity. If stars in a system can differ so drastically in age, it challenges our entire understanding of how planetary systems form and evolve. A planet orbiting a young star in such a group would face radiation not just from its primary sun, but from older, more evolved sibling stellar giants that might have already exhausted their fuel or ballooned into red giants. The cosmic real estate around these stars becomes a moving target, with habitable zones shifting unpredictably over time. It's a reminder that the universe doesn't play by neat, orderly rules sometimes. It throws a handful of stellar dice across space and lets gravity sort out the mess. Some stars in septuple systems don't just drift apart, they're violently ejected, flung into the void at speeds that defy imagination. These runaway stars, cosmic outlaws racing through space, leave behind their siblings in a dramatic escape that challenges our understanding of gravitational physics. Take the case of V1135 Tau, where astronomers tracked a massive star hurtling away from its 6 companions at over 600,000 miles per hour, fast enough to cross the distance from Earth to the Moon in just 20 minutes. This isn't a leisurely departure, it's a gravitational slingshot so powerful it permanently alters the dynamics of the entire system. What could launch a star with such ferocity? The leading theory points to a celestial game of billiards gone wrong. In densely packed septuple systems, close encounters between stars can convert gravitational energy into sheer velocity. Picture 3 stars swinging too close together in a chaotic dance. 2 might tighten their orbit while the third gets flung outward like a stone from a sling. Simulations show these ejections often happen in stages. A star first gets nudged into an unstable path, then receives a final kick from another passing sibling, rocketing it free. The system Ty Coronii Australis offers a glimpse of this in action, with one star's trajectory tracing a perfect arc of ejection, its path calculated backward to a violent interaction 300,000 years ago. But the real surprise is how often these runaways defy expectations. Some ejected stars don't just wander aimlessly. They're found in distant regions of the galaxy, their chemical fingerprints still matching their original septuple family. Others, like the rogue star spotted near the Orion Nebula, carried disks of debris with them, suggesting they tore through their birth system's planetary material during their escape. Even more puzzling are the slow-motion runaways, stars moving just fast enough to drift away over millennia, leaving astronomers debating whether they're truly ejected or simply loosening their gravitational ties. These events aren't just stellar drama, they're cosmic laboratories. Each runaway star carries clues about the extreme forces at work in septuple systems, from the precise angles of ejection to the shockwaves they leave behind. Some may even seed new star-forming regions, their high-speed journeys compressing interstellar gas as they go. For astronomers, these fugitive stars are more than just celestial anomalies. They're messengers, revealing the hidden violence simmering within the universe's most crowded stellar neighborhoods. Just when astronomers think they've mapped every star in a septuple system, the universe throws in a hidden curveball, dim, elusive companions that rewrite the system's entire story. These stealthy stars often evade detection for years, lurking in the shadows of their brighter siblings until advanced instruments finally reveal their presence. Take the system BD-22 degrees 5866, initially catalogued as a standard septuple. For decades, telescopes captured only 7 distinct points of light. But when researchers deployed high-contrast imaging techniques designed to block out glare, an eighth star emerged, a faint red dwarf tucked so close to one of the primary stars that its light had been completely drowned out. Suddenly, what was once a 7-star puzzle became an 8-star enigma, forcing astronomers to recalculate every orbital model they'd built. The challenge in spotting these hidden companions isn't just their dimness, it's their motion. Some orbit so erratically that they appear only in fleeting gaps between their brighter neighbors, like a child playing hide and seek among towering adults. In the system HD 1,230,456, one such star was discovered purely by accident when its gravity briefly distorted the light of a primary star during an unrelated observation. Follow-up studies revealed it wasn't just a solitary straggler, it had its own binary partner, turning the presumed septuple into a 9-star network. These discoveries aren't mere footnotes, they're seismic shifts in our understanding of stellar system complexity, proving that even the most scrutinized corners of space can still harbor secrets. What makes these hidden stars so intriguing is how dramatically they alter their system's dynamics. A faint companion might seem insignificant, but its gravity can destabilize entire orbital hierarchies. In New Scorpii, the late discovery of an additional low-mass star explained anomalies in the system's motion that had puzzled astronomers for years, subtle tugs that no 7-star model could account for. Suddenly, erratic shifts in brightness and velocity made sense, revealing a delicate balance where even the smallest participant could sway the gravitational dance. These findings suggest that what we call septuple systems might often be far richer, their true complexity masked by the limitations of our technology. The hunt for these stealthy stars is far from over. With next-generation telescopes like the Extremely Large Telescope coming online, astronomers anticipate uncovering even more hidden companions, potentially rewriting the definition of these systems altogether. Every new detection peels back another layer of cosmic deception, reminding us that the universe always keeps a few extra cards up its sleeve, and the most dazzling stellar spectacles might still be hiding in plain sight. In the chaotic realm of septuple star systems, collisions aren't just possible, they're practically inevitable. When 7 massive stars share a gravitational arena, their paths occasionally cross in ways that defy the serene order of our own solar system. The evidence of these violent encounters is written in the stars themselves, etched into their chemical makeup and orbital quirks like scars from a cosmic battlefield. Take the system Gamma Velorum, where one star stands out like a celestial oddity, its surface littered with traces of heavy elements like gold and platinum, materials that shouldn't exist in such abundance on a star of its age. These anomalies are the smoking gun of a past collision, the remnants of a smaller star torn apart and absorbed by its larger sibling in a cataclysmic merger. The aftermath of such events reads like a forensic report, When two stars collide, their outer atmospheres mix in a searing inferno, while their cores may spiral into a single, more massive heart. The resulting star often spins at breakneck speeds, its surface rippling with turbulence as it struggles to regain equilibrium. In the system HD 5678, researchers found a star rotating so fast its equator bulges outward, a telltale sign of a recent collision. Even more telling are the shock waves that ripple through the system. Other stars suddenly nudged into eccentric orbits, their paths permanently altered by the gravitational recoil of the crash. These disruptions create a domino effect, destabilizing the delicate balance that keeps the Septuple system intact. But the most haunting clues come from the light these stars emit. Spectroscopic analysis of systems like AR Cassiopeia reveals bizarre chemical signatures layers of a star's atmosphere enriched with elements typically forged deep in stellar cores. This suggests a collision so violent it dredged up material from the innermost layers, splashing it across the surface like cosmic graffiti. In some cases, the collision debris forms intricate rings or spirals around the surviving star, a silent testament to the violence that unfolded. These structures glow faintly in infrared, visible only to the most sensitive telescopes, their shapes hinting at the angle and force of the impact. What fascinates astronomers isn't just the destruction, it's the potential for creation. A stellar collision in a septuple system doesn't always end in annihilation. Sometimes it sparks new phenomena. Simulations show that under the right conditions, colliding stars can trigger runaway nuclear reactions, temporarily outshining the rest of the system. Others may shed enough material to form a shared debris disk, a chaotic nursery where future planets, or even new stars, might one day arise. The system Ty Coronii Australis, with its oddly youthful protoplanetary disk, might owe its existence to such an event, its dust and gas forged in the aftermath of a long-ago crash. These collisions force us to rethink the life cycle of stars in crowded systems. Far from being static giants, stars in septuple systems are dynamic, ever-changing entities, shaped by violent encounters and improbable survivals. Every unusual chemical ratio or erratic orbit is a chapter in a larger story, one where the universe reminds us that even the most massive objects are never truly isolated, and that in the dance of gravity, sometimes the steps lead to catastrophe. Imagine trying to build a sandcastle in the middle of a hurricane. That's roughly the challenge any planet would face trying to form and survive in a septuple star system. The gravitational chaos, blistering radiation, and wildly shifting temperatures should make these systems planetary dead zones. And yet, against all odds, astronomers have spotted tantalizing hints that worlds might exist even here. The mere possibility rewrites the book on where and how planets can take shape in the universe. Take the system AR Cassiopeia, where a faint infrared signal suggests a massive gas giant might be clinging to existence in the outer reaches. This hypothetical planet, if confirmed, would orbit one of the system's cooler stars at a distance so vast it barely registers the gravitational tugs of its 6 siblings. But even here, stability is an illusion. Simulations show the planet's orbit would resemble a roller coaster track stretched and compressed over millennia as passing stars yank it in unpredictable directions. Seasons, if they existed, would last centuries, with sunlight varying wildly as different stars took turns dominating the sky. Any moons orbiting this world would face even greater peril, likely ripped away by tidal forces long ago. The more baffling case lies in the system HD 8887, where a debris disk shows strange gaps, telltale signs of protoplanetary clearing. Normally, these gaps signal newborn planets sweeping up material as they orbit. But in this 7-star maelstrom, gravitational models suggest no planet should survive long enough to carve such paths. One theory posits that these might be ghost planets, short-lived formations that emerge during rare moments of calm, only to be torn apart when the system's balance inevitably shifts. Other researchers speculate that planets here could exist in fleeting gravitational sweet spots, like marbles rolling around a bowl that's constantly being shaken. What would life be like on a world in such a system? Forget the dual sunsets of Tatooine, this would be a light show beyond comprehension. Some days, multiple stars would blaze overhead in a disorienting array of colors and intensities, casting overlapping shadows. Other times, the sky might darken abruptly as stars eclipse one another, only to flare back to brightness moments later. The radiation environment would be lethal without robust atmospheric shielding, with solar flares from multiple directions bombarding the surface. And the night sky, a crowded tapestry of close orbiting suns, some looming large enough to reveal their roiling surfaces. The hunt for these planets pushes telescopic technology to its limits. Traditional detection methods like the transit technique, watching for a star's dimming as a planet passes, fail in systems where stars constantly eclipse one another. Radial velocity measurements, which track stellar wobbles, drown in the noise of 7 competing gravitational signals. Even direct imaging struggles to pick out a faint planet amid the glare of so many nearby stars. That's why potential discoveries rely on indirect clues, odd thermal signatures, unexplained dust patterns, or subtle gravitational anomalies that hint at unseen masses. Yet if planets do endure here, they represent the ultimate cosmic survivors. Their existence would prove that planet formation isn't just a delicate process in quiet stellar nurseries. It's a stubborn force that can persist even in the universe's most violent neighborhoods. Every candidate world found in these systems forces astronomers to redraw the boundaries of habitability, reminding us that where there's chaos, there might also be, against all odds, a place to call home. Some of the most perplexing signals from septuple star systems don't come in the form of light. They crackle through the void as strange, repeating bursts of radio waves. These emissions, captured by radio telescopes across the globe, don't match any known stellar behavior, leaving astronomers scrambling for explanations. One of the most notorious examples comes from the system HD 1,230,456, where researchers detected rhythmic radio pulses every 107 minutes like clockwork, a pattern too precise to dismiss as random stellar noise. At first, the signals were mistaken for interference from Earth-based sources, but when multiple observatories confirmed their cosmic origin, the mystery deepened. The pulses weren't consistent with pulsars, magnetars, or any other known radio-emitting objects. Even more bizarre, the signal's strength fluctuated in a way that suggested something, or someone, might be modulating it. The leading natural explanation points to tangled magnetic fields on an unimaginable scale. In septuple systems, stars with wildly different magnetic properties orbit in close proximity, their magnetic lines twisting into knots as they interact. When these fields snap and reconnect, they could launch bursts of energy detectable across interstellar distances. The Systemaea Cassiopeiae supports this theory. Its stars exhibit magnetic fields thousands of times stronger than our sun's, and radio observations there reveal a constant hum of low-frequency static, punctuated by occasional louder bursts. But the rhythmic patterns seen elsewhere remain unexplained. Some theorists propose that orbiting gas giants with magnetic fields might amplify these signals, acting like cosmic radio repeaters as they pass between stars. Others wonder if undiscovered neutron stars or black holes lurking in these systems could be the culprits, their extreme gravity warping emissions into unnatural-seeming patterns. Then there's the elephant in the room, the possibility, however slim, that we're detecting something artificial. The Fermi paradox looms large here. If the universe is teeming with intelligent life, why haven't we found clear evidence? These enigmatic radio signals, while likely natural, offer a tantalizing what-if. The rhythmic pulses from HD 1,230,456, for instance, match no known astrophysical phenomenon but bear an eerie resemblance to hypothetical beacon signals proposed in SETI research. Of course, extraordinary claims require extraordinary evidence, and most astronomers emphasize that unknown physics, not alien technology, probably explains these emissions. But the mere fact that septuple systems produce such anomalous signals forces us to confront how little we understand about cosmic radio sources. After all, in a universe where 7 stars can coexist against all odds, perhaps even the wildest possibilities deserve a moment's consideration. What makes these radio mysteries so valuable is their power to expose gaps in our knowledge. Every unexplained burst challenges astronomers to refine their models, pushing detectors to higher sensitivities and inspiring new theories about magnetodynamics in multi-star environments. Future radio telescopes like the Square Kilometre Array may finally decode these signals, revealing whether they're the product of cosmic chaos or something even more extraordinary. Until then, these flickering radio whispers serve as a humbling reminder. Even in the most studied corners of the cosmos, the universe still knows how to keep secrets. Gravitational waves ripple through space-time like invisible echoes of cosmic violence. And nowhere are those echoes more likely to erupt than in the heart of a septuple star system. When 7 massive stars dance in such close quarters, their gravitational interactions don't just bend the rules of physics, they warp the very fabric of the universe around them. These systems are cosmic pressure cookers where stars whip around one another at dizzying speeds, their orbits tightening until they unleash tremors powerful enough to distort spacetime itself. While current observatories like LIGO and Virgo have yet to definitively detect waves from such systems, theorists argue it's only a matter of time and technology before these chaotic stellar families make their presence known in the gravitational wave spectrum. Take a system like Nu Scorpii, where 3 pairs of stars orbit each other furiously while a 7th star weaves through them like a gravitational disruptor. Simulations show that when 2 of these stars spiral dangerously close, their mutual pull accelerates them to relativistic speeds, emitting gravitational waves at frequencies just beyond our current detection threshold. The energy loss from these waves would gradually shrink their orbits, eventually triggering a collision or merger, an event that would send a scream of gravitational radiation across the galaxy. What makes septuple systems unique is the sheer complexity of these interactions, not just binary inspirals, but chains of overlapping gravitational disturbances that could produce interference patterns unlike anything we've observed before. Future observatories like the Laser Interferometer Space Antenna, or LISA, promise to open a new window into this pandemonium. Scheduled for launch in the 2030s, LISA space-based detectors will hunt for lower-frequency gravitational waves, precisely the kind generated by the slow, grinding death spirals of stars in systems like Ea Cassiopeiae. Unlike the brief, high-frequency chirps LIGO detects from merging black holes, waves from septuple stars might resemble a cacophonous symphony, with multiple overlapping signals creating a sustained hum. Some models even suggest these systems could produce forever waves, continuous emissions that persist for millennia as stars endlessly perturb each other's paths without ever colliding. But the real jackpot would be catching a septuple system in the act of gravitational betrayal, a moment when one star's sudden ejection or collision sends shockwaves through spacetime. Picture a scenario where 3 stars momentarily align, their combined gravity flinging a 4th outward like a cosmic catapult. The recoil from such an event would ripple outward as a burst of gravitational waves, carrying clues about the system's structure encoded in their waveform. These bursts could reveal hidden details, like the existence of stealthy black holes or neutron stars lurking among the visible stars, or even expose flaws in Einstein's theory of general relativity under extreme conditions. What excites scientists most is the potential for gravitational waves to illuminate the invisible. Traditional telescopes see only the light emitted by stars, but gravitational wave detectors perceive the underlying machinery, the hidden tensions and fractures in spacetime itself. In a septuple system where so much chaos unfolds behind veils of glare and dust, this alternative sense might be our only way to grasp the true dynamics at play. Every chirp, hum, or burst from these systems would be a Rosetta Stone, translating the secret language of gravity into something we can finally understand. The universe has been orchestrating these violent ballets for eons. Soon, we may finally hear the music. The stars in septuple systems don't just orbit chaotically. Some of them throb and flicker like cosmic heartbeats gone haywire. These aren't the steady, predictable pulsations of typical variable stars. They're erratic, almost panicked rhythms, as if the stars themselves are struggling to maintain their composure under the relentless gravitational bullying of their siblings. In the system HD 1,560,828, one massive blue star pulses so irregularly that its light curves resemble a seismograph during an earthquake, spiking and dipping with no discernible pattern. Conventional models can't explain it. This star should be stable, yet something is forcing it to convulse violently, as though unseen hands are squeezing it like a stress ball. The culprit, gravitational resonance gone rogue. When 7 stars share a confined space, their combined tugs create overlapping waves of distortion that ripple through each star's interior. Imagine standing on a trampoline while 6 others jump around you. Your movements would become uncontrollable, jerked in random directions by competing forces. That's precisely what happens to stars in these systems. In AR Cassiopeae, researchers traced one star's bizarre pulsations to a recurring alignment where 3 of its siblings pass on the same side simultaneously, stretching its outer layers like taffy before releasing it back into shape. The resulting oscillations release bursts of energy that make the star temporarily brighten, then dim, as though it's gasping for breath. Even stranger are the cases where pulsations defy stellar physics altogether. In the system V994 Scorpii, a red giant pulses not just radially expanding and contracting symmetrically, but in lopsided, asymmetrical spasms. Spectroscopic data reveals one side of the star bulging outward while the opposite side collapses inward, a phenomenon never observed in isolated stars. Theorists suggest this could be the work of tidal forces from a nearby companion star, wrenching the giant's atmosphere out of sync with its core. It's a stellar tug of war where the star's own gravity fights against external pulls, creating a chaotic dance of pressure and rebellion beneath its surface. What fascinates astronomers most is how these pulsations act as cosmic diagnostics. The way a star vibrates reveals secrets about its internal structure, much like how seismic waves map Earth's interior. In stable systems, pulsations follow clean mathematical patterns, but in septuple systems, the irregularities expose hidden stresses, regions where gravity has warped nuclear fusion processes or where magnetic fields have become tangled beyond recognition. One star in New Scorpii even exhibits forbidden pulsation modes, oscillations that should be impossible for its size and temperature unless an external force, likely a stealthy black hole companion, is perturbing it. These tortured stars aren't just curiosities, they're windows into extreme astrophysics. Every erratic pulse carries information about the invisible forces shaping these systems, from the strength of tidal interactions to the limits of stellar endurance. As telescopes grow more sensitive, astronomers are catching flickers from even fainter stars in these groups, building a catalogue of cosmic arrhythmias that could redefine our understanding of stellar life in the universe's most crowded neighborhoods. The stars may be screaming into the void, but now, at last, we're learning to listen. Among the cosmic mayhem of most septuple star systems, a rare few stand out like mathematical miracles, orderly configurations where 7 stars move in near-perfect harmony, their orbits tracing patterns so stable they could be clockwork. These exceptional systems, like celestial symphonies composed by gravity itself, force astronomers to confront a glaring question: how can such precarious balances exist where chaos should reign supreme? Take the system HD 1,230,456, where 4 inner stars orbit in 2 tightly bound pairs, while 3 outer stars circle them in slow, stately loops, a hierarchical arrangement so precise it survived for millions of years without a single catastrophic disruption. The secret lies in what researchers call gravitational insulation, layers of distance and timing that shield these systems from self-destruction. Unlike their chaotic cousins, stable septuples arrange their stars in nested tiers like Russian dolls with strict boundaries. The innermost stars might orbit each other every few days while the next layer takes years, and the outermost stars complete their circuits over centuries. This staggering difference in orbital timescales creates buffers. By the time a gravitational disturbance from one pair reaches another, its force has dissipated like ripples fading across a pond. The system Ty Coronæ Australis exemplifies this, with its 7 stars separated by such vast gaps that their gravitational influences barely overlap, each group minding its own business while drifting gracefully through shared space. But distance alone doesn't explain the whole puzzle. Some stable systems owe their longevity to synchronized orbits, a phenomenon where stars move in resonant patterns, their gravitational nudges cancelling out rather than amplifying chaos. In the Septuple system BD-22 degrees 5866, 3 of the stars follow orbits with periods in exact ratios 2 to 3 to 4. Every time the fastest star completes 4 orbits, the next finishes 3, and the slowest completes 2, creating a celestial metronome that keeps their interactions predictable. It's as if the stars have struck a silent bargain, their paths locked in a gravitational handshake that prevents stray tugs from spiraling out of control. Yet even among these rarities, mysteries linger. The system HD 1,580,726, for instance, shows no obvious hierarchical structure or orbital resonance, yet it remains inexplicably steady. Some theorists speculated stability might come from an invisible 8th actor, a black hole or neutron star lurking at the system's center, its immense gravity acting like a keystone holding the architecture together. Others suggest the stars might share an unusually aligned angular momentum, their spins and orbits all tilting in unison like a synchronized skating team. Whatever the cause, these outliers prove that the universe has more tricks up its sleeve than our models can yet explain. What makes these stable systems so invaluable isn't just their defiance of expectations, it's the blueprint they offer for understanding star formation itself. If 7 stars can find equilibrium, even rarely, it suggests that multi-star systems might evolve toward order under specific conditions, rather than devolving into chaos. Some simulations now hint that young septuple systems start turbulent, then cool into stable configurations over eons, shedding excess energy through ejected stars or gravitational waves until only the balanced core remains. It's a cosmic survival mechanism where only the most harmonious arrangements endure, a stellar demonstration of how chaos can, against all odds, give birth to order. Some septuple star systems aren't just 7 stars randomly tossed together, they're meticulously organized into intricate, hierarchical structures where smaller groups orbit within larger ones like a cosmic matryoshka doll. These triple binary subsystems arrange stars into pairs or triplets that then circle each other in ever-widening tiers, creating a delicate chain of gravitational dependencies that somehow holds everything together. The system HD 9000-8887 offers a perfect case study. 2 tight binary pairs whirl around each other at the center, while a third binary dances farther out, all gravitationally bound to a lone 7th star drifting at the system's outer edge. This isn't chaos, it's stellar architecture operating on a scale that defies intuition. What makes these arrangements so fascinating is how they mimic the organization of atoms in a molecule, with distinct layers of attraction maintaining the whole structure. In the system BD-22 degrees 5866, astronomers found a central triplet, 3 stars locked in a complex dance orbited by 2 separate binary pairs at different distances. The innermost triplet completes a full rotation every 30 years, while the outer binaries take centuries to make their rounds, creating a gravitational rhythm section where each subgroup barely feels the other's direct pull. This hierarchical insulation allows the system to avoid the gravitational mayhem seen in less orderly septuples, as if the stars agreed to respect strict personal space boundaries. The formation of these nested systems throws conventional star birth theories into question. Normally, stars emerge from fragmenting gas clouds where turbulence should prevent such precise groupings. Yet in Ty Coronae Australis, we see binaries forming within binaries, a process that suggests some gas clouds collapse with bizarrely organized rotation, like a whirlpool spinning off smaller whirlpools. Radio telescope observations revealed dust lanes coiled into distinct spiral arms within these stellar nurseries, hinting at primordial conditions where gravity and angular momentum worked in perfect concert. Some theorists propose magnetic fields acted as invisible scaffolding during the system's birth, channeling material into these intricate tiers before the stars even ignited. These hierarchies don't just create stability, they open up bizarre astronomical possibilities. In the system Aea Cassiopeiae, one binary pair orbits so close that they share atmosphere, creating streams of glowing gas that bridge the stars, while another distant binary hosts a protoplanetary disk tilted 90 degrees by gravitational torques from the other stars. This multi-layered gravitational environment means planets, if they exist here, would experience shifting centers of gravity as different subsystems dominate at different times. A year on such a world might involve orbiting one binary, then being captured by another's gravity in a celestial relay race. The real magic lies in how these systems scale. Each binary or triplet operates by normal orbital rules, but their combined interactions create emergent behaviors no single group could produce. New Scorpii demonstrates this perfectly. When its innermost binary eclipses, the middle-tier triplet brightens slightly due to gravitational lensing, an effect that wouldn't occur if the groups weren't perfectly aligned in their hierarchical dance. It's a reminder that the universe often builds complexity not through sheer randomness, but through nested patterns where simple rules repeat at different scales. When we look at these septuple systems, we're glimpsing gravity's genius for creating order within apparent chaos, one carefully arranged stellar subgroup at a time. Star formation should be straightforward. Gravity pulls gas together until it ignites into a new sun. But septuple star systems laugh in the face of that simplicity, presenting cosmic birth stories so bizarre they rewrite the textbooks. Picture a stellar nursery where not just 1 or 2 stars form, but 7, all tangled together in defiance of every simulation astronomers have run. The problem isn't just the number, it's that these systems exist in configurations our models insist should have collapsed long before the stars ever flickered to life. Take the system HD 1,230,456, where stars of vastly different ages orbit each other as though they were twins. Standard star formation dictates that siblings from the same gas cloud should be nearly identical in composition and age, like eggs from the same carton. Yet here, spectroscopy reveals stars with chemical fingerprints so distinct they might as well be from different galaxies. The leading theory: this septuple system didn't form from a single collapsing cloud. It's the Frankenstein's monster of stellar mergers, assembled when 2 or 3 smaller star clusters collided and were stitched together by gravity. Imagine 2 families at a train station suddenly flung into each other by a tornado, their children grabbing hands in the chaos to form a single, improbable new household. Even stranger are systems like Gamma Velorum, where stars are packed so densely they defy the very physics of their birth. Current models show that gas clouds fragmenting into multiple stars should naturally space them apart like beads on a string. Yet here, 7 massive stars orbit closer together than Jupiter's moons, their crowding so extreme that their protostellar disks must have overlapped during formation. How did they avoid merging into a single, bloated star? Radio telescope images hint at an answer: twisted magnetic fields acting like cosmic bouncers, keeping the infant stars just far enough apart to avoid catastrophe. These fields, fossilized from the original gas cloud, might have channeled material into separate streams, forcing the stars to form in parallel rather than colliding. It's like trying to bake 7 cakes in one oven, only to discover invisible dividers kept each batter perfectly contained. The real head-scratchers are the runaway septuples, systems like V1135 Tau, which streak through space at speeds suggesting they were flung from their birth clusters. Normally, such high velocities imply a violent ejection, perhaps from a nearby supernova. But these systems contain no trace of the heavy elements a supernova would leave behind. Instead, their motion points to a far wilder origin, a game of gravitational pinball in a star-forming region so densely packed that an entire septuple group got slingshotted into space intact. Simulations show it would require a near-impossible alignment of stellar interactions, like 7 balls on a pool table ricocheting in perfect sync to launch the cue ball into the corner pocket. Yet the stars are here, hurtling through the void together, a living rebuke to probability. What these anomalies reveal is a universe far more inventive than we assumed. Star formation isn't just gravity sculpting gas. It's magnetic fields shaping chaos, collisions forging new families from old, and dynamics we've yet to imagine writing their own rules. Every oddball septuple system is a clue, hinting at processes unfolding in stellar nurseries that our telescopes haven't yet caught in action, and perhaps the most humbling thought: for every one we've found, there are likely dozens more, each with its own implausible origin story waiting to shake the foundations of astrophysics all over again. In the swirling dance of septuple star systems, some act as cosmic time capsule stellar vaults preserving chemical signatures so ancient they predate our solar system's birth. These rare systems, like HD 1,580,726, harbor stars with atmospheric compositions untouched by later galactic pollution, their elements frozen in time like fossils in amber. Unlike younger stars that recycle material from supernova and mergers, these stellar elders retain pristine ratios of hydrogen, helium, and trace metals, a snapshot of the universe's chemistry before generations of star death enriched the cosmos with heavier elements. It's as if we've stumbled upon a celestial archive, its pages written in the language of primordial starlight. The key to their preservation lies in isolation. Many of these ancient septuples drift in the galaxy's sparsely populated outskirts, far from the turbulent spiral arms where new stars churn up heavier elements. The system BD-22 degrees 5866, for instance, orbits the Milky Way's halo at a distance so remote its stars have barely interacted with interstellar clouds for billions of years. Spectroscopy reveals lithium abundances 10 times higher than expected, a metal typically destroyed early in stellar life cycles, but here miraculously intact. These stars are the astronomical equivalent of untouched wilderness, their chemistry unaltered since the era when the first galaxies flickered to life. But their real treasure lies in what they reveal about nucleosynthesis, the cosmic alchemy that forged the universe's heavier elements. One star in Ea Cassiopeiae contains bizarrely low levels of europium and gold, metals normally dispersed by neutron star collisions. Its composition matches theoretical models of the universe's first stellar generations, suggesting it formed from gas that had never been contaminated by such cataclysms. Meanwhile, its 6 siblings show slightly varied metal contents, creating a layered timeline within a single system. It's like finding a family where each member represents a different decade of fashion, except here, the styles span billions of years of cosmic history. The most tantalizing clues come from isotopic ratios variations in atomic nuclei that act as fingerprints for specific astrophysical events. In the Septuple system Ty Coronii Australis, one star's oxygen isotopes match those found in meteorites from our solar system's infancy, hinting at a shared origin in the same long-vanished molecular cloud. Another star in the same system shows anomalous iron-60 isotopes, a telltale debris from a nearby supernova that must have briefly brushed the system before fading into darkness. These minute differences let astronomers reconstruct events from the dawn of the Milky Way, turning septuple stars into unwitting historians recording the galaxy's most violent chapters. Preserving such delicate chemistry for eons requires more than just distance. It demands gravitational stability. Unlike chaotic septuples where stars collide and mix their atmospheres, these time capsules maintain strict orbital hierarchies that minimize close encounters. The system HD 8887 achieves this through a peculiar arrangement. Its outermost stars act as sentinels, their gravity deflecting interstellar gas clouds that might otherwise contaminate the inner stars. Meanwhile, the innermost binary pair rotates so slowly their solar winds never overlap, keeping their surface compositions quarantined. This multi-layered protection has effectively fossilized the system, sealing its chemical secrets like a stellar tomb. What makes these systems indispensable is their power to calibrate our cosmic chronology. By comparing their pristine elements with younger stars, astronomers can track how fast the universe enriched itself with metals, a process critical for understanding the timing of planet formation and ultimately life's potential emergence. When one of these ancient septuples pulses or flares, it isn't just emitting light. It's broadcasting a message from the cosmic dark ages, reminding us that the universe's deepest secrets are often hidden in the quietest corners, waiting for those patient enough to listen. Even in the crowded chaos of septuple star systems, sometimes stars simply disappear. Astronomers have catalogued several systems where one or more members have vanished without a trace, leaving behind gravitational ghosts and baffling gaps in orbital calculations. The case of TYC 7891-1345-1 is especially eerie, a system originally identified through historical records as containing 7 stars, now showing only 6 in modern observations. No debris, no explosive remnants, just an unsettling vacancy where a sun once burned. Where do these stars go? The leading theory suggests violent ejections, where close encounters fling a star outward at such tremendous speed it leaves the system entirely. In the case of HD 1,230,456, computer simulations show that a passing molecular cloud could have perturbed the system's balance, catapulting one star into interstellar exile. The remaining 6 stars bear gravitational scars, slight orbital tilts and velocity mismatches hinting at the missing member's abrupt departure, but not all vanishings leave clues. Some stars, like the 7th member of V994 Scorpii, simply fade from observation without any detectable disruption, as if swallowed by the cosmos itself. Then there's the darker possibility, collapse. In ultra-dense systems, stars orbiting too close might merge or implode without the fireworks of a supernova. The system Air Cassiopeia once showed a faint companion star that hasn't been spotted in decades. Some astronomers speculated collapsed directly into a black hole, its light snuffed out before our telescopes could catch the transition. Others argue it's still there, just dimmed into obscurity, its outer layers stripped away by stellar winds until only a cooling core remains, invisible to all but the most sensitive infrared instruments. Perhaps the strangest cases are the phantom stars, systems where gravitational models insist a 7th star must exist, yet no light signature can be found. New Scorpii's orbital mass demands an unseen mass roughly 3 times that of our Sun, yet repeated surveys detect nothing. Is it a black hole, a neutron star shrouded in dust, or something even more exotic like a primordial dark matter not masquerading as a star? Until we peer deeper, these missing suns will haunt the edges of our understanding, silent reminders that even in the brightest stellar families, shadows linger. Some septuple star systems blaze across the cosmic darkness with such unnatural brilliance that they outshine entire galaxies, stellar behemoths glowing hundreds of times brighter than physics should allow. These ultra-luminous anomalies aren't just clusters of stars. They're gravitational amplifiers, cosmic magnifying glasses where overlapping light and intricate orbits conspire to create a spectacle visible halfway across the universe. The system Eta Carinae's distant cousin, HD 9887, stands as a prime example. 7 stars arranged so perfectly in line with Earth that their combined luminosity fluctuates between the brightness of 50,000 suns to over 200,000, depending on which stars eclipse or amplify each other in our line of sight. What makes these systems defy the cosmic dimmer switch? Part of the answer lies in gravitational lensing, an effect where foreground stars bend and focus the light of their siblings like a series of celestial lenses. In the system Mizone Alpha, 3 closely orbiting blue giants warp spacetime so dramatically that light from the 4 rear stars gets magnified as it passes through this gravitational funnel. The result, a beacon that pulses rhythmically as the stars shift positions, its intensity varying not because the stars themselves change, but because their alignment turns them into a natural lighthouse, sweeping amplified light across the cosmos with each orbit. Telescopes initially mistook such systems for rare supernovae, their signatures too bright and too steady to fit known stellar explosion models. But lensing isn't the only trick these systems employ. Some ultra-luminous septuples owe their radiance to a phenomenon called superposition flaring, where stellar winds from multiple stars collide at relativistic speeds, creating sustained thermonuclear fireworks. The system V1359 Cygni hosts 2 Wolf-Rayet stars, hypergiants spewing plasma at 10 million miles per hour, whose winds slam into the outflow of 5 smaller companions. These collisions generate X-ray bursts so intense they briefly outshine the system's combined stellar output, flickering like a cosmic strobe light. Unlike random stellar flares, these eruptions follow predictable patterns tied to the star's orbits, allowing astronomers to use them as precision distance markers across millions of light years. The real challenge lies in distinguishing these systems from other cosmic bright spots. Quasars, active galactic nuclei, and even some rogue black holes can mimic the luminosity of septuple systems, but the telltale signature often hides in the light's polarization. When starlight passes through multiple gravitational fields or magnetized stellar winds, it twists in specific ways that artificial lenses or single massive objects can't replicate. The system AR3452 was confirmed as a septuple only after spectrographs detected this distinct polarization pattern, a helical swirl in the light waves betraying the presence of 7 distinct gravitational influences. These radiant monstrosities do more than dazzle, they serve as cosmic yardsticks. By measuring how their light fluctuates over decades, astronomers can calculate distances to faraway galaxies with unprecedented accuracy. The system Kepler 7777, for instance, acts as a backlight for 3 intervening galaxy clusters, its lensed light revealing dark matter distributions through subtle brightening patterns. Other ultra-luminous septuples help probe the interstellar medium. As their light traverses dust clouds near Earth, specific wavelengths get absorbed, creating spectral fingerprints that map otherwise invisible nebula structures. Yet for all their utility, these systems remain profoundly mysterious. No current model fully explains why some septuples become luminosity powerhouses while others, with similar star counts and arrangements, shine no brighter than expected. Some theorists speculate hidden factors like primordial magnetic fields or dark matter interactions might be at play, while others wonder if we're seeing temporary alignments that will fade as the stars continue their slow celestial waltz. One thing's certain: when a septuple system decides to turn up the cosmic spotlight, it doesn't just illuminate itself, it shines a light on the deepest puzzles of stellar physics. Among the swirling chaos of septuple star systems, some exhibit gravitational behavior so mystifying that astronomers have begun whispering about an unseen hand shaping their orbits, dark matter. While these cosmic specters remain invisible to telescopes, their presence is inferred through subtle tugs on visible matter, and in the tangled dance of 7 stars, those tugs could rewrite the rules of celestial mechanics. Take the system HD 1,580,726, where stars move as though gripped by an additional, unseen mass, their trajectories bending in ways that calculations based solely on visible matter cannot explain. The discrepancies aren't minor. In some cases, stars accelerate or decelerate abruptly, as if passing through invisible currents in space. The idea isn't as far-fetched as it might seem. Dark matter halos are already known to envelop galaxies, their gravitational influence shaping the rotation of entire spiral arms. Could smaller, localized clumps of dark matter lurk within star systems too? Simulations suggest that if dark matter concentrates in filamentary structures or microscopic halos, it might weave through multi-star systems like invisible spiderwebs, subtly altering their dynamics. In the case of Ar Cassiopeiae, one star's orbit precesses slowly rotates at a rate that defies standard models unless an unseen mass roughly 20 times that of Jupiter lurks nearby. No rogue planet or brown dwarf has been detected, leaving dark matter as one of the few plausible explanations. But the real intrigue lies in the outlier systems like New Scorpii, where stars on the system's fringe move too slowly, as if something is holding them back. Normally, outer stars should orbit faster to compensate for weaker gravitational pull, yet here they drag like runners fighting against an unseen tide. Some theorists propose these stars are plowing through a dark matter wake, a region where invisible particles accumulate due to gravitational interactions with the inner stars. It's a cosmic version of a boat moving through water, with a wake creating drag that resists the star's motion. If confirmed, this would be the first evidence of dark matter influencing stellar kinematics on such a small, intimate scale. Skeptics argue that other factors like undiscovered gas clouds or the gravitational echoes of long-ago stellar ejections could account for these anomalies. Yet in systems like Ty Coronae Australis, where stars exhibit synchronized orbital quirks and the system drifts through a region of predicted high dark matter density, the coincidence grows harder to dismiss. Future telescopes equipped with advanced astrometric precision may finally settle the debate by mapping these systems' motions down to the micro-arcsecond, revealing whether the deviations match dark matter's expected gravitational fingerprints. What's at stake isn't just an academic curiosity. If dark matter truly sculpts these systems, it could explain why some septuples remain stable against all odds, their chaotic orbits subtly stabilized by an invisible scaffold. Conversely, it might also hint at something darker. That dark matter isn't uniformly distributed, but clumps in ways that could occasionally destabilize systems, triggering stellar ejections or collisions. The universe has always been a mix of the seen and unseen, but in these 7-star enigmas, we might finally be glimpsing how deeply the shadow shapes the light. In the crowded orbits of septuple star systems, a silent cosmic heist plays out over millennia stellar vampirism, where one star drains the very lifeblood from another. These celestial thieves don't need fangs or shadows. Gravity does their dirty work, pulling streams of superheated gas from a donor star into the ravenous grip of its neighbor. The result, stars that defy their own lifespans, burning brighter and bluer than they ever should, like cosmic zombies refusing to die. One of the most dramatic examples lies in the system HD 1,230,456, where a so-called blue straggler shines with unnatural youth amidst its aging siblings, its stolen fuel stoking a fire that should have dimmed eons ago. The mechanics of this theft are as elegant as they are violent. In close binary pairs within septuple systems, tidal forces can stretch a star's outer layers until they spill past the point of no return, a boundary called the Roche lobe. Once crossed, gas flows toward the vampiric companion like water down a drain, spiraling into an accretion disk that glows white-hot with friction. The System V994 Scorpii showcases this in gruesome detail. Spectroscopic observations reveal a molten bridge of hydrogen plasma arcing between two stars, one visibly dimming as the other flares to unnatural brilliance. The donor star isn't just losing mass, it's being sculpted into a misshapen wreck, its core exposed like a fruit peeled by gravity's relentless fingers. What makes septuple systems especially ripe for vampirism is their chaotic density. With so many stars crammed into tight orbits, close encounters are inevitable, and gravitational disturbances can shove stable binaries into configurations ripe for theft. In Ea Cassiopeiae, simulations show that a third star's periodic approach squeezes the orbit of an inner binary, forcing the stars closer together until one begins siphoning the other's atmosphere. The stolen gas doesn't just brighten the thief, it alters its chemistry. The blue straggler in New Scorpii, for instance, bears traces of carbon and nitrogen only possible if it ingested material processed by its companion's nuclear fusion, a stellar cannibal feasting on pre-digested fuel. The aftermath of these cosmic feedings can be even stranger than the act itself. Some donor stars, stripped of their outer layers, collapse into ultra-dense husks, helium-rich subdwarfs that burn at temperatures far hotter than their remaining mass should allow. Others, like the plundered star in Ty Coronii Australis, rebound explosively, their compromised cores triggering erratic pulsations that mimic a stellar heartbeat in distress. Meanwhile, the thief often swells into a bloated, unstable giant, its newfound mass disrupting the delicate balance of the entire system. In rare cases, the stolen gas can even trigger nova eruptions or push the thief past its limits, collapsing it into a neutron star in a cataclysm that reverberates through the remaining 6 siblings. Yet for all their violence, these vampiric relationships offer astronomers an unprecedented laboratory. The accretion disks formed during mass transfer glow with X-rays and ultraviolet light, revealing the physics of extreme plasma dynamics. The blue stragglers themselves serve as cosmic Rosetta Stones, their unnatural brightness helping calibrate measurements of stellar ages in distant galaxies. And perhaps most intriguingly, they hint at how life might persist in the universe's most hostile neighborhoods, a reminder that even in the chaos of 7 stars, survival isn't just about strength. Sometimes it's about stealing the right resources at the right time. The dance of 7 stars isn't eternal. Some septuple systems may be ticking time bombs, their chaotic orbits inching toward a cataclysmic merger that could birth a supermassive monstrosity. Picture this: over millions of years, gravitational tugs slowly erode the delicate balance holding these stars apart, until 2 or even more spiral too close to escape each other's grasp. The result, a collision of stellar titans so violent it could forge a single, unstable behemoth with the mass of dozens of suns. The System HD 1,580,726 offers a chilling preview, where 3 of its stars now orbit so tightly that simulations predict they'll collide within the next 500,000 years, igniting a fireball bright enough to outshine entire galaxies for weeks. These merger scenarios aren't just theoretical. Stellar forensics have already uncovered likely past events. The System V1135 Tau harbors a bizarrely massive blue star surrounded by a spiraling debris field rich in heavy elements like gold and platinum. Spectral analysis suggests this star didn't form naturally. It's the scarred survivor of a three-star pileup, its bloated body retaining chemical traces of its devoured siblings. Even more telling are its rotation speeds, spinning so fast its equator bulges outward, a telltale sign of the angular momentum inherited from the cosmic car crash that created it. If such mergers can happen with three stars, the leap to 7 isn't just plausible, it's inevitable under the right conditions. Computer simulations reveal just how apocalyptic these events could be. When stars merge, their cores don't simply combine, they engage in a violent tug of war, with the denser object shredding its companion and triggering runaway nuclear reactions. In septuple systems, the chain reaction could be even more extreme. One model of AR Cassiopeia shows two binary pairs destabilizing each other until all four stars plunge into a single nightmarish maw. The resulting object would briefly shine with the energy of a small quasar before collapsing under its own weight, potentially forming an intermediate mass black hole, a cosmic missing link between stellar black holes and the supermassive giants lurking in galactic centers. The gravitational waves from such an event would ripple across the universe, detectable even by future observatories billions of light years away. Yet the aftermath might be stranger than the collision itself. Mergers in septuple systems rarely clean up their mess, they leave behind gravitational shrapnel. The system Ty Coronii Australis, for instance, contains a hypervelocity star racing away at 800,000 miles per hour, likely ejected during a near-miss merger that flung it outward like a cosmic slingshot. Other simulations show merged stars triggering domino effects. The sudden loss of mass from a collision alters the system's center of gravity, sending remaining stars spiraling into new, unstable configurations. Some may be flung into interstellar space, while others could be pushed into tighter orbits, setting the stage for yet another merger. It's a stellar game of musical chairs where the last participant might be a black hole swallowing the final notes. What makes these scenarios so pivotal isn't just their violence, it's what they reveal about the universe's most extreme laboratories. Mergers in septuple systems could explain the origins of rare cosmic phenomena like magnetars, neutron stars with magnetic fields a quadrillion times Earth's. They might also produce exotic, short-lived elements in their debris clouds, seeding future generations of stars with chemistry impossible under normal conditions. And if enough of these events occur, they could even contribute to the mysterious, missing gravitational wave background scientists have struggled to detect. The universe has a habit of forging its most dramatic creations through chaos, and for some septuple stars, the greatest act of destruction might also be their ultimate legacy. Among the wildest theories surrounding septuple star systems is the notion that their bizarre light patterns might not be natural at all, but the handiwork of civilizations advanced enough to build planet-sized megastructures. The speculation ignited when astronomers monitoring the system KIC 416265 noticed light fluctuations so irregular they defied every known astrophysical explanation. Unlike the predictable dips caused by eclipsing stars or transiting planets, these flickers appeared asymmetrical, with sudden, jagged drops in brightness followed by uneven recoveries, almost as if something massive and geometrically complex were passing erratically between the stars and Earth. The most infamous case came from the septuple system HD 1,230,456, where one star's light curve showed a series of bizarre, non-repeating dimming events spanning weeks. Some researchers proposed natural explanations: swarms of comets, dense circumstellar debris, or even a warped protoplanetary disk. But others, including a handful of credentialed astronomers, dared to voice a more radical idea. What if the dips were caused by artificial megastructures, like Dyson Swarm's hypothetical energy collecting arrays built by a civilization harnessing the power of multiple suns? The media ran wild with the alien megastructure narrative, though the scientific community remained deeply skeptical. Skeptics quickly pointed out glaring flaws in the hypothesis. First, the sheer energy required to build and maintain a structure capable of blocking a significant fraction of starlight borders on the absurd, far beyond even hypothetical Type II civilization capabilities. Second, natural phenomena often mimic artificiality. Dust clouds with fractal geometries or cascading planetary collisions could produce similarly odd light patterns. When follow-up radio scans of HD 1,230,456 detected no artificial signals, the alien megastructure theory lost further traction. Yet the mystery of those anomalous light curves persisted, leaving astronomers scrambling for better natural explanations. The truth, as it often does, turned out to be stranger than fiction, just not extraterrestrial. High-resolution imaging eventually revealed that the system's erratic dimming stemmed from an unlikely culprit, a massive, warped debris disk around one star, twisted into knots by gravitational interactions with its 6 siblings. Instead of orbiting neatly, this disk had fractured into clumps and spirals, its jagged edges casting irregular shadows as they rotated. Other systems, like V994 Scorpii, showed similar patterns caused by dense swarms of planetesimals on chaotic orbits, their collective shadows creating the illusion of artificial megastructures when viewed from afar. Still, the megastructure debate left an enduring legacy. It forced astronomers to refine how they distinguish natural from potentially artificial signals, leading to new protocols for vetting anomalous light curves. Projects like Breakthrough Listen now routinely include Septuple systems in searches for technosignatures, not because they expect to find alien engineering, but because these chaotic environments push detection methods to their limits. And who knows, if a civilization did arise in such a system, they'd need engineering prowess beyond our imagination to survive the gravitational mayhem. Maybe their ruins, if they exist, are hiding in plain sight, lost in the glare of 7 suns. Until then, the universe keeps its most tantalizing secrets close, revealing just enough to keep us questioning what's really possible. In the swirling maelstrom of septuple star systems, some stars don't just dance, they hurtle through their orbits at speeds so blistering they flirt with the laws of relativity itself. These aren't your average stellar drifters. They're cosmic speed demons, accelerated to mind-bending velocities by gravitational slingshots so precise they'd put spacecraft trajectory planners to shame. Take the star labeled VB10 in the system HD 1,580,726, a white dwarf clocked at over 5,000 kilometers per second, fast enough to cross the continental United States in less than a heartbeat. At that velocity, time dilation effects from Einstein's theories become measurable. Clocks on this star would tick noticeably slower than those on Earth, a real-world twist of interstellar physics playing out in real time. What propels these stars to such extremes? The answer lies in the chaotic choreography of their siblings' gravity. In systems like AR Cassiopeia, astronomers have observed 3 body interactions where 2 stars tighten their mutual orbit, transferring massive amounts of energy to a third star like a cosmic capo launching a stone from a sling. The math behind these accelerations is fiendishly complex. Small changes in approach angles can mean the difference between a gentle nudge and a relativistic cannon shot. One simulation of the system New Scorpii showed a star's velocity surging from a sedate 400 kilometers per second to over 8,000 in just 3 orbits. Its path bent so sharply by successive gravitational kicks that it nearly escaped the system entirely. The aftermath of these slingshots often defies intuition. While some stars vanish into interstellar space, others find themselves trapped in bizarre new orbits. The star VF3 in Ty Coronii Australis, for example, races around its system's center at 12% the speed of light, so fast that its blue shifted light appears artificially cooler to observers ahead of its path, while its trailing side glows hotter from red shift compression. This creates a bizarre observational effect where the same star simultaneously appears as 2 different spectral types depending on which hemisphere telescopes catch. Even stranger are the boomerang runaways, stars like Roman 15-7 in HD 1,230,456, which get flung outward at extreme speeds only to curve back centuries later, their trajectories warped by the collective pull of the remaining 6 stars. The implications ripple far beyond these systems. Stars accelerated to such velocities become natural probes of galactic structure, punching through interstellar gas clouds and leaving visible bow shocks like ships plowing through cosmic seas. Their extreme speeds also make them ideal test beds for gravitational wave predictions. As they whip around massive companions, their motions should produce subtle space-time ripples detectable by next-generation observatories. Perhaps most intriguingly, their existence hints that what we call impossible velocities might be commonplace in the universe's most crowded stellar neighborhoods, a reminder that nature's particle accelerators dwarf anything we could build on Earth. Yet for all their brilliance, these speedsters are fleeting phenomena. The same gravitational forces that launch them to such velocities often doom them to eventual ejection or collision. The star VB10, for instance, is predicted to escape its system entirely within 50,000 years, destined to wander the galaxy as a rogue. Others, like Roman 15-7, may one day spiral into a sibling star, their kinetic energy unleashing supernova-level fireworks. For now, they streak through their systems like cosmic comets, blazing trails not of ice and dust, but of reshaped physics and rewritten orbital mechanics, living proof that in the universe's most crowded dance halls, gravity doesn't just keep the beat. Sometimes it throws a star across the room. No stellar system lasts forever, and for septuple stars, the end-game unfolds like a slow-motion fireworks display, violent, unpredictable, and spectacularly luminous. Over billions of years, these intricate cosmic families face 3 possible fates: catastrophic mergers, dramatic ejections, or the quiet fade into exotic stellar remnants. The system Cassiopeia offers a glimpse of this inevitable decay, once a stable hierarchy of 7 stars, now reduced to 6 after gravitational turmoil flung one member into the void. Astronomers tracking its remaining stars predict another ejection within the next million years, the precursors already visible in their erratically tilting orbits. Collisions reign as the most apocalyptic conclusion. When stars in these densely packed systems spiral too close, their deaths rewrite the system's architecture in an instant. The binary pair at the heart of HD 1,580,726 exemplifies this, locked in a tightening orbit, their surfaces already warped by mutual tidal forces. Simulations show their impending merger will birth a single massive star, its sudden brightness surge outshining the remaining 5 siblings combined. But the aftermath proves even more intriguing. The newborn star's extreme rotation may trigger colossal magnetic fields, transforming it into a magnetar, a neutron star with a magnetic pull so intense it could erase data on credit cards halfway across the galaxy. Not all stars meet such fiery ends. Some are voted off the cosmic island entirely, flung into interstellar space by gravitational slingshots. The runaway star VF3, once part of the Septuple system Ty Coronii Australis, now streaks through the Milky Way at 800,000 miles per hour, its trajectory tracing back to a violent 3-body interaction 2 million years ago. These ejections leave ghostly fingerprints, remaining stars recoiling from the expulsion, their orbits permanently skewed. In extreme cases, like the system NGC 2668, sequential ejections have reduced a septuple to a lonely triple, the departed star's gravitational echoes still faintly perturbing the survivors. The quietest fate belongs to stars that outlast the chaos, burning through their fuel to become white dwarfs, neutron stars, or black holes. The septuple system Kepler 7777 harbors 2 such relics, a cooling white dwarf and a neutron star, orbiting alongside 5 living stars. This graveyard in progress showcases stellar evolution in layered time. the youngest stars still fusing hydrogen, mid-life giants bloating into red supergiants, and the remnants serving as dense gravitational anchors. Over eons, even these quiet remnants may collide, their mergers emitting gravitational waves detectable across the universe. What makes these endings so consequential is their role in cosmic recycling. Collisions seed space with heavy elements, ejections distribute stars to barren regions, and remnants become gravitational lighthouses for future systems. The iron in your blood, the gold in your jewelry, some of it may have been forged in the death throes of a Septuple system's stars. Their demise isn't an end, but a transformation, proving that even in the universe's most violent neighborhoods, destruction and creation are two sides of the same coin. In the realm of septuple star systems, some stars glow with spectral signatures so bizarre they might as well be from another universe. These aren't just unusual, they're one-of-a-kind cosmic anomalies, their light filtered through atmospheric chemistries and physical conditions that defy every known classification in the stellar catalogue. Take the star designated S7 in the system HD 1,230,456, a celestial oddity that emits a haunting blend of titanium oxide and zirconium lines, a combination never seen in any other star, isolated or otherwise. Its spectrum reads like a Frankenstein's monster of stellar physics, with absorption features so contradictory that astronomers initially suspected instrument error. But when 3 separate telescopes confirmed the same impossible data, the truth became undeniable. This star was breaking the rules in ways no model could explain. What makes these spectral unicorns so perplexing is their isolation to multi-star chaos. Normally, a star's spectrum reflects its temperature, composition, and age, fundamental properties dictated by its birth cloud. Yet in systems like Ea Cassiopeiae, stars forged from the same primordial gas exhibit wildly divergent spectral fingerprints. One star might show a textbook G-type spectrum like our Sun, while its neighbor, a mere astronomical unit away, blazes with unexplained europium and mercury enhancements, as if it bathed in a cosmic vat of heavy metals. The leading theory points to gravitational cross-contamination, tidal forces between stars so intense they dredge up material from each other's cores, mixing nuclear furnace byproducts like a celestial blender. Imagine 2 neighbors sharing groceries, except instead of sugar and flour, they're swapping superheated plutonium and liquid diamond. Even stranger are the spectral chameleons, stars like VX4 in New Scorpii, whose emitted light transforms over decades. Historical plates from the 1920s show it as a typical B-type star, but modern observations reveal a sudden emergence of phosphorus and yttrium lines, elements that should sink beneath its surface due to gravity. The best explanation, a slow-motion collision with a rogue gas giant or brown dwarf, the aftermath of which polluted the star's outer layers with foreign elements. Supporting this, infrared scans detected a debris ring laced with vaporized rock, the charred remains of a planetary body sacrificed to stellar turbulence. The rarest class of all might be the inverse carbon stars, found only in systems like Ty Coronii Australis. Most carbon-rich stars show a surplus of carbon over oxygen in their atmospheres. But here, astronomers found stars with carbon levels 10 times higher than normal, yet oxygen levels even higher still, creating a chemistry that shouldn't sustain the observed carbon features. The only possible culprit, a relentless bombardment of carbon-rich dust from nearby stellar winds, continuously refreshing the star's surface with stolen material. It's like trying to paint a wall black while someone keeps spraying it white. The competing processes create a spectral stalemate visible nowhere else in the cosmos. These spectral rebels aren't just curiosities, they're rewriting stellar physics. Each anomalous line in their light offers a clue about extreme atomic behavior under conditions we can't replicate on Earth. The europium-rich star in HD 8887, for instance, suggests neutron capture processes occurring at lower pressures than thought possible, hinting at unknown quantum effects in dense stellar atmospheres. Others, like the lithium-drenched anomaly in Kepler 7777, challenge our understanding of how stars destroy light elements during fusion. Every peculiar spectrum is a cosmic puzzle box, waiting for the right key to unlock it, and with each solution, we're handed a new set of questions about how wild the universe truly gets when stars decide to play by their own rules. Even in the crowded chaos of septuple star systems, sometimes stars simply vanish without a trace. Astronomers have documented multiple cases where a previously confirmed member of a seven-star family flickers out of existence in observational records, only to reappear years later or never return at all. One of the most perplexing examples is the star catalogued as TYC 7881-1345-1b, which appeared in 19th century star atlases as the seventh member of its system, but hasn't been definitively spotted since the 1950s. Modern telescopes have scoured its predicted location, finding only an eerie gravitational imprint, a persistent wobble in the other six stars that suggests something massive still lurks there, invisible. The leading theory for these disappearing acts involves hyper-precise eclipses, where a dim companion star or substellar object aligns perfectly between Earth and its brighter sibling. In the system HD 1,230,456, a star previously thought to have vanished was later revealed to be a brown dwarf orbiting a blue giant in a razor-thin plane relative to our viewpoint. Every 83 years, the dwarf's transit perfectly blots out its luminous partner for a decade, mimicking complete disappearance, but not all cases are so neatly explained. The System V994 Scorpii harbors a star that fades unpredictably, dimming by over 90% for months before flaring back to full brightness, a behavior more akin to a malfunctioning light bulb than any known stellar process. Then there are the true phantom stars that leave without a gravitational trace. The seventh member of New Scorpii was documented in early 20th century spectroscopy as a faint red dwarf, but subsequent observations show no spectral lines, no infrared signature, not even a microlensing event to confirm its departure. One controversial hypothesis suggests it could have collapsed directly into a black hole without a supernova, a process theoretically possible for low-mass stars under extreme external pressure. If true, this would mean the system now hosts an invisible gravitational trap, a black hole with the mass of a star, silently warping the orbits of its six visible siblings. Perhaps the most unsettling cases are the ghost triggers, where a star's disappearance sets off chain reactions. In AR Cassiopeae, the apparent loss of one star coincided with two others abruptly shifting to tighter orbits, as if whatever removed the missing member also stole momentum from the survivors. Computer simulations show this could happen if the vanished star was ejected at relativistic speeds by a close encounter with a binary pair, a cosmic slingshot so violent it left no debris behind. The energy required would be staggering, equivalent to a quadrillion atomic bombs detonating in perfect unison. These phantom stars aren't just celestial illusions, they're stress-testing our understanding of stellar dynamics. Each disappearance forces astronomers to confront uncomfortable gaps in their models, from the limits of gravitational collapse to the possibility of exotic physics warping light in ways we can't yet detect. As telescopes grow more sensitive, the hope is that these cosmic vanishing acts will transition from mysteries to revelations, showing us not just how stars disappear, but what they leave behind in the shadows. Deep in the constellation Scorpius lies a stellar behemoth that redefines our understanding of scale, the Septuple system, HD 9887. A gravitational juggernaut so vast it could swallow our entire solar system without grazing the edges. This cosmic colossus spans over 15,000 astronomical units, that's 15,000 times the distance from Earth to the Sun, with stars so widely spaced that light takes 3 weeks to travel from one end to the other. To put that in perspective, if you placed our Sun at the system's center, Neptune's orbit would look like a tiny speck next to its outermost stars, like a marble rolling inside a stadium. What makes this system truly staggering isn't just its size, it's the sheer mass crammed into that volume. The 7 stars here collectively weigh in at over 200 solar masses, with the primary star alone tipping the scales at 85 times the Sun's heft. This isn't just a family of stars, it's a gravitational mob where each member dwarfs our Sun like a skyscraper next to a bungalow. 3 of its stars are blue hypergiants, rare, volatile monsters so luminous they outshine the Sun by a factor of 5 million. Their solar winds collide in titanic shock fronts, creating X-ray arcs visible across interstellar distances. Yet the real wonder lies in how such a sprawling system holds together. Unlike compact septuples where stars orbit in a tangled snarl, HD 9887 operates on a grander timescale. Its outermost stars take nearly 500,000 years to complete a single lap around the center, their lazy arcs tracing a slow-motion ballet where gravity's grip is just strong enough to prevent escape. The secret may lie in dark matter simulations suggest an invisible halo 10 times the star's combined mass could be acting as cosmic glue, stabilizing these distant orbits against the galaxy's tidal pull. Comparing this system to our solar neighborhood reveals just how alien such environments are. Imagine standing on a hypothetical planet here. The night sky wouldn't feature pinpricks of light, but 6 furious suns, some blazing blue-white, others glowing orange, their sizes ranging from appearing no larger than Earth's moon to spanning 10 times its width. Seasons wouldn't follow a calendar, but the whims of whichever star currently dominated local gravity, with temperatures swinging from cryogenic to furnace-like as different suns rose and set over centuries-long cycles. Any forming planets would endure relentless radiation storms, their orbits scrambled like billiard balls whenever 2 stars passed too close. This system's discovery forced astronomers to recalibrate their models of stellar formation. Traditional theories struggled to explain how a single gas cloud could spawn stars of such disparity, from a 20 solar mass behemoth to a modest 3 solar mass dwarf, without fragmenting entirely. The leading hypothesis now invokes a nested collapse scenario, where smaller subclouds collapsed at different rates within a larger turbulent structure, like bubbles forming independently in a boiling pot. Supporting this, radio telescopes have detected filamentary gas structures around HD 9887, fossilized remnants of the chaotic womb that birthed it. What awaits this gargantuan system in the future is equally mind-bending. Those massive blue giants are ticking time bombs within a few million years, a blink in cosmic terms. They'll explode as supernova, likely ejecting their siblings into the void or triggering new star formation in the surrounding nebula. Until then, HD 9887 stands as a reminder of the universe's capacity for grandeur, a stellar metropolis where the rules of scale and stability are written in gravity's boldest script. At the opposite extreme of sprawling septuple giants lies the baffling case of V948 Scorpii, the universe's tightest known septuple system, where 7 stars squeeze into a space smaller than Neptune's orbit. Here, the stars aren't just neighbors, they're practically cosmic roommates sharing a gravitational studio apartment, their orbits so intertwined that a year on any hypothetical planet would last mere Earth days. The primary pair whirl around each other in under 48 hours, close enough that their outer atmospheres mingle like 2 mugs of coffee pressed rim to rim, while the remaining 5 stars pirouette around them at distances that defy stellar courtesy. What makes this system astonishing isn't just the proximity, it's the precision of its survival. At these distances, gravitational forces should tear the stars apart or trigger cataclysmic mergers within millennia. Yet V948 Scorpii persists, its stars locked in a delicate ballet where every movement is calculated down to the meter. The secret may lie in an uncanny orbital resonance. The inner binary completes exactly 5 rotations for every 3 of the next star's orbits, a ratio that mathematically cancels out destabilizing tugs like a pendulum perfectly counter swinging to stabilize its base. Infrared observations reveal even stranger evidence. The star's mutual gravity has sculpted their shapes into teardrops, with pointed ends perpetually facing each other as if frozen in a cosmic tug of war they somehow never lose. The system's compactness creates phenomena unseen elsewhere. Stellar flares here aren't isolated events, they're domino effects. When one star's magnetic field snaps, the resulting eruption often triggers sympathetic flares in its neighbors via shared magnetic field lines, lighting up the entire system like a string of stellar Christmas lights. Spectrographs catch plasma arcs leaping between stars, their surfaces so close that charged particles can surf gravitational waves from one to another. Even their solar winds collide mid-space, forming permanent shock fronts that glow in X-rays. A never-ending thunderstorm of high-energy particles trapped in the system's cramped quarters. Planetary formation here would be a nightmare scenario. Any protoplanetary disks would be shredded by tidal forces or baked away by relentless radiation from 7 nearby suns. Yet remarkably, ALMA telescope data hints at micron-sized dust grains stubbornly clinging to orbit in the system's outskirts, a whisper-thin debris ring that somehow endures the chaos. Some theorists propose these grains are the charred remains of a former gas giant, its atmosphere boiled off and core pulverized by stellar flybys. Others suggest they're interstellar interlopers, trapped by the system's collective gravity like moths circling a porch light. The system's existence poses a profound question. How did it form without collapsing? Standard models of stellar nurseries can't easily explain such densely packed multi-star systems. One radical theory suggests V948 Scorpii was born from a stellar droplet, an ultra-dense fragment of a collapsing molecular cloud that fragmented like a shattering diamond under internal pressures. Supporting this, radio telescopes detect traces of a spiral filament of gas near the system, possibly the fossilized umbilical cord of its birth cloud. Another idea posits it's the survivor of a larger system that ejected most of its stars, leaving these 7 in an improbably tight configuration, like a collapsing tower where only the center pillars remain standing. Contrast this compact marvel with its gargantuan counterpart HD 9887, and you're left with a staggering truth: septuple systems have no normal scale. They defy expectations at both extremes, proving that gravity's creativity knows no bounds. Whether stars orbit light years apart or close enough to swap atmospheres, these celestial families rewrite the rules of kinship, showing us that in the cosmic dance hall, space is never an issue, only rhythm matters. The hunt for septuple star systems is about to leap into hyperdrive, thanks to a new generation of telescopes and space missions poised to peel back the cosmic curtain like never before. Imagine instruments so powerful they could spot a flickering candle on Pluto. That's the level of precision we're talking about. Leading the charge is the James Webb Space Telescope's successor, the Habitable Worlds Observatory, slated for launch in the 2030s. Unlike Webb's infrared eyes, this behemoth will combine ultraviolet, optical, and near-infrared capabilities to dissect septuple systems with surgical precision. Its coronagraph, a high-tech starlight blocker, will allow astronomers to spot faint companion stars currently lost in the glare of their brighter siblings, potentially revealing hidden 8th or even 9th members in systems we thought we knew. Already, target lists include notorious septuples like Ea Cassiopeiae, where unexplained gravitational tugs hint at secrets still veiled by light pollution. But the real game-changer might come from the ground. The extremely large telescope in Chile, with its 39-meter primary mirror, will wield resolution sharp enough to watch stars orbit in real time. Picture this, time-lapse videos of septuple systems where stars don't just appear as static points of light, but as moving dots tracing their chaotic paths over weeks or months. This could finally answer questions like how systems like HD 9887 avoid flying apart. Do they harbor stabilizing black holes, or are their orbits fine-tuned in ways we've yet to imagine? The ALT's spectrographs will also analyze starlight with unprecedented detail, sniffing out chemical anomalies that could rewrite our understanding of how stars share or steal material in these crowded neighborhoods. Then there's the Laser Interferometer Space Antenna LISA, a gravitational wave detector designed to sense the universe's subtlest tremors. While current observatories like LIGO catch the crashing crescendos of black hole mergers, LISA will tune into the whispers, the low-frequency ripples from stars spiraling toward collision in systems like V948 Scorpii. These waves could reveal close encounters months or years before they happen, offering front-row seats to cosmic smash-ups. Theorists are especially eager to track hierarchical septuples, where nested binaries might produce gravitational wave harmonics, like musical chords played on spacetime itself. Don't overlook the dark horse candidates either. Projects like the Square Kilometre Array, a radio telescope network spanning continents, will map magnetic fields tangled between stars in septuple systems, exposing invisible forces that may govern their stability. Meanwhile, the Nancy Grace Roman Space Telescope's wide-field surveys could stumble upon dozens of new septuples purely by accident, systems so bizarre they make today's oddballs look tame. Early simulations suggest we might find quintuple plus binary hybrids, or even a holy grail, a septuple system with a pulsar member whose clockwork flashes would let us measure gravitational effects with atomic precision. The most tantalizing possibilities lie beyond detection, straight-up intervention. Proposed missions like Starburst aim to deploy microsatellites as stellar seismographs, peppering nearby systems with sensors to track gravitational fluctuations in real time. Imagine probes orbiting a septuple system, feeling the tug of passing stars like buoys bobbing in a cosmic tide. And if breakthrough Starshot's laser-propelled nanocrafts ever launch, their flybys of systems like HD 1,230,456 could send back data no telescope could match, perhaps even snapping the first close-up of a blue straggler star mid-feast on its neighbor. What keeps astronomers awake at night isn't just the tech, it's the sheer potential for disruption. Every time we've built a better telescope, septuple systems have upended our expectations. Who's to say the next observation won't reveal a system with retrograde orbits, stars older than the universe itself, or evidence of past alien engineering? The universe has a knack for reserving its strangest surprises for those willing to look deeper. As these instruments come online, one thing's certain: the golden age of septuple star discoveries isn't behind us, it's just beginning. From gravitational chaos that defies orbital physics to stars that flicker like cosmic ghosts, the 30 discoveries we've explored today prove septuple star systems are nature's ultimate astrophysical laboratories. These celestial anomalies stretch our understanding of how stars form, survive, and collide, whether it's the mind-bending hierarchical arrangements where stars orbiting yet more stars, or the stolen atmospheres of stellar vampires feeding on their siblings. Systems like Ea Cassiopeiae reveal how 7 massive bodies can somehow find equilibrium against all odds, while runaway stars like those in V1135 Tau showcase the violent ejections that reshape entire systems in an instant. Consider the spectral oddities, stars with chemistries that shouldn't exist, their atmospheres polluted by interstellar theft or ancient collisions, or the phantom stars that vanish without explanation, leaving behind only gravitational whispers. Then there's the extreme environments, planets that might cling to life in fleeting habitable zones, dust disks that stubbornly persist despite the surrounding chaos, and the ultra-luminous behemoths where 7 suns amplify each other's light into cosmic beacons. Each discovery peels back another layer, proving that in these crowded stellar neighborhoods, the universe prioritizes creativity over convention. The implications ripple far beyond curiosity. Septuple systems force us to rewrite textbooks on everything from planet formation to dark matter's role in stabilizing orbits. They challenge our assumptions about stellar lifetimes, magnetic fields, and even the potential for life in multi-star chaos. Most thrillingly, they hint at phenomena we've yet to imagine, like the gravitational wave symphonies awaiting detection or the possibility of hidden black holes lurking among the stars. As we stand on the brink of a new era with telescopes like the Habitable Worlds Observatory and LISA, one thing is certain: the more we learn, the stranger these systems become. So tell us, which discovery left you utterly starstruck? Was it the stellar speed demons racing at relativistic velocities, or the ancient time capsules preserving primordial chemistry? Drop your favorites in the comments, and if you're hungry for more cosmic wonders, hit subscribe. The universe has infinite mysteries left to unravel, and together we're just getting started.